This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Our first speaker is Dar Gilboa from Google Quantum AI. So Dar, please go ahead.
Thanks. Hi, so I'm Dar. I'll be speaking about our work, Exponential Quantum Communication Advantage in Distributed Inference Learning. This is joint work with Chagai Michaeli, Daniel Sudri, and Jared McLean. So this is an exciting time for quantum computing, given that quantum error correction is starting to work in practice. So this is an example from a few months ago where you see a 2D surface code logical qubit, and you see that the logical error rate decays exponentially with the distance of the code. And so you could ask, well, what happens if this actually scales up and you're able to build a large fault-tolerant quantum computer? So what could you do with such a device? So we all know this sort of canonical killer app, which is quantum simulation, and there are a few possibly interesting applications that would use this capability. And additionally, you'd have exponential speedups for some structured problems, and factoring being the most canonical example. But you could ask, will quantum computers be useful even more generally? And this is a question that Scott Aronson phrased in 2015 when he asked, will the impact of quantum computers rival that of classical computers in the previous century? And you could ask even a more modest question, could they somehow rival the impact of GPUs in the last decade or so? And I would argue this is more or less equivalent to asking whether quantum computers will be useful for processing classical data, just because the vast majority of data that people care about is classical. It doesn't come from the quantum world. And Aronson gives a pretty pessimistic answer to this question. And one of the main issues is the data loading problem. Essentially because if you look at the typical computation that you do in classical machine learning, the computation time is usually polynomial in input size. And this is the case, for instance, in neural network training and inference. And there are a few ways to see this. If you think about overparameterization, what it more or less tells you is that the non-convex problem of training a neural network becomes somehow well-behaved once the number of parameters is larger than the input size. And then because the training time is proportional to the number of parameters, you get this polynomial dependence between the two. And some more evidence for this are these neural scaling laws that are well known for large models, including LLMs, that basically say that the test loss for these models scales like some power law in the data set size and the number of parameters. And the big issue is, of course, that loading n classical bits onto your quantum computer takes time about n, or space-time volume n, to be precise. And so if you have some algorithm that has log n runtime, you lose your speed up just because of the cost of loading the data. And this is different from problems where we believe there's a potential for exponential speed up. These are problems that are sort of compute limited, like factoring or maybe combinatorial optimization, where we believe the best classical algorithms actually have runtime exponential in the input size. And so you might wonder, well, what about quadratic speedups? So these are known for some very generic problems like unstructured search, MCMC, and optimization. The issue with those is that there's a huge cost of running anything on a quantum computer that comes from error correction. So there's a paper from a few years ago that tried to quantify this by comparing the cost of implementing a NAND gate on a classical computer and quantum analog, which is a Toffoli state in the 2D surface code. And they find that there's a gap of about 10 orders of magnitude in terms of the space-time volume of these two computations. And this implies that essentially you need an enormous instance size to get any practical advantage from a quadratic, like asymptotic speedup. So I would say this 10 orders of magnitude it's a little out of date. So the recent results on T-state elevation, which is an idea of Craig Gidney, is that could probably reduce this down by a couple of orders of magnitude, but it's still going to be like an 8 orders of magnitude difference. And so you might wonder, okay, well, is this whole idea of doing something interesting with classical data hopeless? I would argue that not necessarily. So if you sort of go back to the classical competition and look at progress in classical machine learning, it often doesn't come in the form of speed-ups. And actually, if you look at the biggest breakthroughs in the last few years, they come from rather better parallelization. So things like disbelief, the use of GPUs or transformers are actually, they've been so successful because they enable better parallelization, and transformers are actually worse in terms of their time complexity because they scale quadratically with like the sequence length, and so they're actually worse compared to previous models, but they're easier to parallelize. And then, so when you're in this highly distributed setting, you actually have to trade off between sort of various resources, and time being one of them, but there's also space, communication, and a bunch of other things. And if you look at sort of, there are these famous plots of the compute time of like large neural networks showing this exponential growth, you see that a lot of it can be explained if you look at the degree of parallelization in terms of like the number of GPUs that are used to train these models. And the interesting thing is that there are known quantum advantages in terms of some of these resources that aren't time complexity or query complexity. Things like memory and communication. And you could ask, well, are any of these relevant for classical machine learning problems? And we show that some of them are, at least. And specifically, we work in the setting of communication complexity. So this is a setting where you have two parties exchanging messages, and they want to compute some function of both of their inputs. And we only care about the total communication that they need to do this, either quantum or classical. We don't necessarily care about computation complexity, but in the cases we consider, it's only going to be polynomially worse than the classical analog. And the nice thing about this setting is there's additional structure there that you don't have when you're thinking about, say, query complexity or time complexity. And this allows you to actually prove unconditional exponential quantum advantage in terms of communication. So this is impossible to dequantize, and you don't even have to make any hardness assumptions or anything like that. And there's also a natural connection to space complexity, because you can sort of imagine that you have this problem with multiple parties, but think of the two parties as sort of the same party at different points in time. And then if you have a lower bound on the amount of communication, it implies a lower bound on the memory that you need to solve a problem, which could allow you to prove space advantage as well. And the advantages we consider are going to be a result of amplitude encoding. So essentially, we're going to be in this setting where Alice has n classical bits. She encodes them in the amplitudes of a quantum state using log n qubits, and communicates a state like this to Bob. And so you could ask, well, how does such a state compare to log n classical bits? So Halevo's bound says that you can only sort of transmit log n bits of information. On the other hand, there are known examples where you can get exponential communication advantages by encoding data in this way. So it's not exactly trivial. Like in some sense, this is stronger than just log n classical bits. And so in terms of the sort of classical motivation here, so distributed computation is very common in classical machine learning. So if you're trying to train a large neural network or use it for inference, these models basically require tens of thousands of devices to store at this point and to train. They sometimes don't even fit on a single data center. So Gemini, for instance, which is Google's latest LLM, was trained on multiple data centers in parallel. And they were like tens of kilometers apart. And essentially during training, the nodes in such a network have to communicate intermediate features or gradients. And this is also true during inference. And this can lead to communication bottlenecks, essentially. And specifically, so there are lots of ways to sort of break down a model like this when you're doing distributed computation. We'll focus on what's known as pipeline parallelism, which is sort of illustrated here. This situation where you want to compute a composition of some functions, and you store sort of different functions on different devices. And if you were trying to just compute such a function or compute its gradients, you need to essentially communicate features between different nodes. And so we'll be working with a simple quantum analog of this setting. And I see that, PowerPoint has some trouble converting my Google Slides. But yeah, this is just some quantum state that's a function of the input. And essentially, it's a standard parameterized quantum circuit, but we split the parameterized unitaries between two players, and we imagine that these two players can communicate quantum states. And then the output of the model will be some expectation value of some observer below. And so we'll be working in a regime that corresponds to scaling in classical machine learning, which is that the number of parameters is polynomial in the input size. This is what we get when we say train a fully connected neural network. And we assume that the depth, so like the number of unitaries here, is much smaller than it's logarithmic essentially in the size of the input, which is also pretty common standard machine learning models. And it turns out that for this problem, there's an exponential, or at least for this model, if you look at two problems, so just estimating the gradients and doing inference, so estimating this expectation value, which we call f. For both these problems, you get an exponential communication advantage. So essentially, any classical algorithm will require a number of bits that's polynomial in n and p. These are the two large numbers in our problem, the input size and the number of parameters, while we give a quantum algorithm that requires a number of qubits that is only polynomial in n and p. So how do we show this? There's sort of two pieces. So we need a classical lower bound, showing that you need a lot of communication classically, and a quantum upper bound. The classical lower bound is based on what's known as the vector in subspace problem. It's a problem that was introduced by Raz in '99. It's a problem where Alice is given a vector, Bob is given two orthogonal subspaces, and you have a promise that the vector lies close to one of these subspaces. So this is like an example in 2D. And the goal of the players is to figure out sort of, which is the case. And it turns out that this problem requires a lot of classical communication, requires square root of n bits. On the other hand, there's a very simple quantum algorithm that involves Alice just encoding her input in the amplitudes of a quantum state, sending it over, and Bob does a simple measurement. And you can prove an exponential communication advantage in this way. So what we do is we reduce basically vector and subspace to either inference or gradient estimation with our model. And this implies that both those problems are as hard as this problem, and so the lower bound just carries over. Now our quantum upper bound is just based on this well-known connection between the problem of estimating gradients and estimating a set of expectation values. So here for each parameter, we get sort of a quantity like this that we need to estimate. And this can be related to the shadow tomography problem. And famously, this only requires, so if you want to estimate p expectation values of two active observables, this only requires a number of copies of an unknown quantum state that's logarithmic in the number of observables. And there's recent work by Amira Abbas, Robbie King, and Robert Wang that showed how to adapt shadow tomography to this problem of estimating gradients of a parameterized quantum circuit. And they're concerned specifically with the scaling with the depth of the circuit. But one sort of nice feature of their result is the total number of qubits they need is logarithmic in the number of parameters and the size of the input n. And what we do is we take their algorithm and just extend it to the distributed setting. And that's how we get our upper bound. And so you might ask, okay, well, maybe this is just a trivial consequence of amplitude encoding. You could always get such an exponential space advantage. Well, we show that, space advantage and a corresponding communication advantage, we show that this isn't the case by considering linear classification. So this is sort of like a very well-known classical problem. So essentially the learning problem, the corresponding inference problem are very well studied. So here Alice and Bob each receive a vector. One can be thought of as the data, and the other is the model, which is just a simple linear model. And when you have a margin in this problem, there's some parameter that essentially lower bounds the magnitude of the inner product between these vectors. And so linear classification with a margin is a problem of figuring out the sign of the inner product, given that there's some lower bound on its magnitude. And it turns out that for this problem, we basically give a quantum lower bound and a classical upper bound on the number of bits or qubits you need to communicate. That implies that the problem becomes easy if the margin is large, but it becomes too hard if the margin is small, and there's actually no gap in between. So for this problem, communication, an exponential communication advantage is impossible, even though you could take the inputs here and amplitude encode them. And we also sort of explore some regimes beyond a single sort of step of gradient descent. So up to now, I was talking about the task of just estimating the gradient, but we could also think about the entire training process. So if we're in a setting where, for instance, the entire model is frozen and you only train the last layer, which is common when you want to train a classifier over some pre-trained features, in that case, we can actually cast the entire training problem as a shadow tomography problem, because it also sort of works in this online setting. And we get a logarithmic dependence on the total training time in terms of the amount of communication that you need. And we also show that this generalizes to other algorithms. Some of them are more efficient than a shadow tomography-based algorithm. For instance, there's this paper of Harrow and Knapp's that defines a sort of stochastic coordinate descent algorithm, and we show that we can adapt this to the distributed setting as well and get better scaling in some regimes. And so what I've talked about up to now was just sort of in terms of this pretty generic looking circuit. And you could ask, okay, well, does this apply to circuits that implement useful functions that can sort of compute meaningfully with classical data? And we show that this is indeed the case. So just to kind of set this up a bit, everyone's probably familiar with convolutional neural networks. The reason that they're so successful is that they essentially bake in this natural symmetry to translations that natural images have. So essentially, you would want an image classifier to be insensitive to certain image transformations, like translations. And if you have a network that involves convolutions and pooling, the function that you learn is sort of naturally invariant to these types of transformations. And this leads you to learn smoother classifiers that generalize better. And this idea naturally applies to other geometries as well. So you can sort of take the convolution and think of it as a multiplication by what's known as the circulant matrix here, which I denote by C. And then think of the analogous operation where instead of the Euclidean geometry that you have for images, you have some non-Euclidean geometry, just defined by the adjacency matrix of a graph. And then the natural analog of the circulant matrix becomes the adjacency matrix. So here I have like two examples of these matrices. And so this is the sort of linear operation in these models. And this is a basis for what are known as graph CNNs. And they're sort of the go-to approach when you want to compute over graph data. And you can apply them to solve all kinds of problems, including like node level problems, like node classification or graph classification, and basically a bunch of things listed here. And what we do is we study a shallow graph CNN. So specifically, we have a model that looks like this. So we have our adjacency matrix here. This matrix X is a matrix of features that live on nodes of the graph. So they're sort of illustrated by these vectors here. Then you have these two weight matrices, and there's a quadratic nonlinearity and a pooling operator. And then the final output is given by some trace over this thing. And what we show is, for this model, first of all, our exponential communication advantage still holds. So specifically, we consider a setting where Alice holds the node features, so this matrix X. Bob holds the adjacency matrix and the weights of the model, and only Alice is allowed to send messages. So we show that essentially you could run inference with log n qubits of communication, but essentially a classical algorithm would require square root of n bits. And this is based on a reduction from the F Boolean hidden partition problem. On the other hand, this model actually performs well on standard benchmarks. So we took this model, and then we can just train it as if it was a standard machine learning model. And we train it on a bunch of tasks, node classification tasks and graph classification. And there are a lot of numbers here, but the main takeaway is just that we compare our model to state-of-the-art graph CNNs on a bunch of data sets, and we find equivalent performance, sometimes even outperforming some of these other models. And these are large, like standard benchmarks, so they contain like graphs with millions of nodes and hundreds of features. For example, you have this graph of Reddit posts where each node corresponds to a post, and each edge corresponds to a user that commented on both posts, and you want to sort of classify the nodes based on sort of different categories. Or in this graph classification task, you have some complicated protein, and you want to sort of figure out some property of this protein, whether it's an enzyme or not. And so, yeah, like the bottom line here is that we, it seems tricky to get exponential speedups with classical data because of this issue that I mentioned earlier. On the other hand, if you look more broadly beyond speedups and query complexity advantages, you can find exponential speedups for pretty generic tasks in machine learning, which is what we show for communication complexity for this task of inference and gradient estimation. And we show that this also holds for models that actually look like realistic neural networks and perform well on standard benchmarks. I think more broadly, there are sort of interesting directions to explore in this space. Essentially, because you can use quantum resources in all these interesting ways, one example is a result that we also presented here as a poster, which is work with Sid Jain, UT Austin, where we showed that in this setting of distributed computation, you can provably prevent data from being reused when you're considering certain computational tasks. And you could also ask about sort of other types of non-computational advantages in, say, like space, latency, privacy, and a bunch of other things. And we're actually planning to organize a workshop sort of around these questions within the next year. And I think that this is sort of these are interesting questions to ask because they sort of might end up giving us some indication of whether quantum computers will be useful as a specialized research tool or as sort of something more general, more widely applicable. Yeah, that's my talk. I'd like to thank my collaborators again, and thank you for your time.
So, questions? Yep. Is there a...
So on your one of slides, you mentioned many other aspects where quantum computation can be beneficial, but you haven't listed the energy consumption.
Yeah, I mean, I have some thoughts on this as well. Yeah, I think that's because essentially unitary computation, okay, so the energy cost of computation is related to irreversibility, and quantum computation is inherently reversible. So there may be interesting, an interesting potential for energy advantage as well. Like it's something that is definitely, worth thinking about more. Yeah, I agree.
Yeah, question over there.
Thank you very much. Thank you very much. A really interesting talk. Can you give us a scale of how much of an LLM training is actually in communication?
Sure. So this is sort of it's a bit of a tricky question to answer because these details are typically not disclosed by the people who train these models. And actually, even within Google, it's sort of cordoned off. Like, I don't even have access to this information. But basically, if you look at what people do, is there are different ways to split up a large model. So this is known as like pipeline parallelism, but there are other ways to break up a model. You can say take a large linear algebra computation and break up a matrix into submatrices and sort of distribute different submatrices to different nodes and then combine the result. For example, this is known as tensor parallelization. And different types of parallelization have different communication overheads. And what you typically have to do is you need to like design your computation in a way that sort of takes those into account. Like you can't really break things up arbitrarily. You need to sort of take into account that you have like much lower bandwidth interconnect, say between data centers or between like clusters of GPUs. And in principle, if you had exponential savings, you might be able to access like a larger design space when you're trying to do this sort of trying to break up the computation.
More questions? Yeah, back there.
Okay, so what's the motivation for studying distributed quantum neural networks in shallow models, given that communication overhead in such models can well shadow any sort of advantage?
Okay, so these models aren't shallow. So yeah, I mean, I agree with you in the sense that if you have shallow models, you can't get an exponential quantum advantage in communication just because you have efficient descriptions of the circuits. When I say, you know, shallow here, I mean like, you know, you have to go like back and forth like log L number of times, but actually each one of these unitaries has to be deep, has to be very deep to get the advantage.
Okay, since I have the mic, what you're exchanging is still classical gradients, right? What is being exchanged when you're
communicating quantum states. You have a quantum interconnect.
But what is being exchanged is the gradients, right?
Well, gradients or features, yeah, like intermediate features.
Okay.
More questions?
Hi, thanks. Super good talk. On this last slide you had, you mentioned this workshop. I guess your messages were like very nice top-down, like coming from solid machine learning theory and then seeing how we can, like where quantum can help. Can you give any perspectives on the bottom-up, like given the quantum machine learning models that people have been presenting in this conference, where would you put them in this diagram, if any?
Where do I put them? Yeah, I mean, I think I would say that the models we consider, they look very different because, I mean, they're deep and they would require error correction. Like, I don't think, you know, none of this seems viable to me in like the NISQ regime or anything close. Yeah, I would say that the distributed setting does sort of like open up some interesting new angles that where like efficient circuits might be sort of useful. So for instance, this consumable data paper that I mentioned, it's interesting because it's in a distributed setting, but it's also strategic. So you have like two parties and they have different objectives. And actually in those settings, there might be a regime where you can get away with shallow circuits, but shallow circuits that you can't actually learn their efficient description unless you're given it ahead of time, which is sort of related to some of these hardness of computational hardness of learning results that you know were in this paper that Laura worked on, Laura Lewis. So those are maybe a little closer to, you know, like nearer term quantum circuits.
Okay, in the interest of time, I think we'll stop here. Let's thank Dar again.